develop membrane reactors both in gas phase and in liquid phase, much more in the next following course in the fall semester. This will be one of the areas where there will be some specific attention. But today, in this course, I would just like to introduce what we are talking about and which are the field of major interest. And you can see here, we are talking about membrane reactors, but also membrane bioreactors. And membrane bioreactors is the field where there is much more activity today and also industrial success. In this country, you have been developing these membrane bioreactors for wastewater treatment. There are hundreds, thousands of membrane bioreactors installed in Korea, and that's all around the world. For municipal wastewater treatment, for some industrial water treatment. All these applications, as always, are just the umbrella and very well accepted in the logic of the process intensification that we have been discussing. In Europe, membrane bioreactors for industrial application, for wastewater treatment, are considered BAT, best available technology. So you are supposed to utilize as much as possible this kind of technology for sure in some wastewater treatment. And big cities are already introduced membrane bioreactors in the overall municipal wastewater treatment. In Italy, to give you an example, we have cities as Prato or Brescia or a place near Venice where everything is related to membrane bioreactors for the wastewater treatment. And this is, we have been discussing about this, but that's an example of what we are talking about. The conventional wastewater treatment at the municipal wastewater particularly, you see is a little bit complicated system where you have different units, one after the other. You have some from the raw materials, you have some coarse pretreatment, some coarse filtration, you have a primary clarifier, you have activator sludge, you have secondary clarifier, you have sand filter, disinfection, etc., etc. And finally, you have sludge dewatering disposal, sludge digestion, and so on. If you are introducing a membrane bioreactor today, these 1, 2, 3, 4, 5, 6, 7, 8 units are becoming 3, in principle. You can just have a rough pretreatment to separate the suspended solids eventually. But after you just go in the membrane filtration where you combine the filtration with the chemical conversion. And that is, as you can see here, just you can see the difference. You can reduce from 8 steps to roughly 3, 4 steps. That is one of the motivation for the interest in this kind of application. All membrane reactors, membrane bioreactors, or reactors just with no bio involved, can be realized with different kind of configuration. And generally, you can assume these 2 different ways of doing. One way is just to have a traditional reactors, can be bioreactor in the case we are discussing, and you integrate the traditional reactors with an external membrane operation. Most part of the system running today, this external membrane operation is ultrafiltration or microfiltration. So you integrate these 2 different steps in one, they are related, and you have continuous recycle. You can, the membrane units just separate the effluent, that can be clean water, from some concentrate, retentate, and this retentate is recirculated in the initial bioreactors. That is a way of doing, and is a way to facilitate the operation. In principle, in the first point that if you remove continuously the product of your reaction, if this reaction will never arrive to equilibrium. You will have, when you are approaching equilibrium, you're removing the product, you will have irreversible system. So the system will continue until, in principle, 100% of your substrate is converted. If you don't have this, at one point, this system, you arrive to some equilibrium system, and then you have to stop the operation. So that is the way of doing. And as I was mentioning, this is mainly ultrafiltration or microfiltration. However, today, smart membrane engineers are studying and realizing new kind of reactors of this kind, where this is no more just ultrafiltration. Here you can have everything. You can introduce a membrane contactors. That can be membrane distillation. Here it can be just electrodialysis, can be reverse osmosis, and similar. So the systems are becoming more and more sophisticated and complicated. And that's on the situation in which you have side stream this external one. You can have another system in which in the case of these membrane bioreactors, the module, the ultrafiltration unit, is submerged, is immersed in the bioreactor itself. That was the one interesting, relatively recent idea from some colleague from Japan. They invented these, what they are called now, membrane bioreactors submerged. And this relatively simple idea made a lot of innovation in the field, because doing this way, you can control some of the parameters that normally are killing your process, particularly when you are working in a system with high level of contamination, high viscosity, and municipal wastewater normally are not easy to be handled. And the fouling control in this way is much easier. And we will see, that is, as you know, is one of the problems we have. So you can have a system as this one, but also a system where bioreactors and the membrane unit is a single step. You see only single box. In the box, there is the biological reactors and the membrane system inside. In this case, what is normally, the system is working in such a way that you make a vacuum inside the module. So you just have the transformation, the biotransformation taking place outside the module, and you making vacuum inside the membranes. Fresh water, the clean water is penetrating the membranes, and you extract just clean water from here. And that is a way to basically to minimize on one side fouling problem, as you will see. There is some help here with this bubbling of air. And in the meantime, in the logic of PI, for example, easy, that is the footprint of the system is much more smaller. There are single units instead of then two units. So that is another immediate advantage of the system. So this is one of the most interesting case in the membrane reactors, because this case, as I mentioned before, in Europe is BAT, best available technology, and all around the world there are today thousands and thousands of these units running, including Korea. You will see some of the largest company in the world, as I don't know, General Electric is now active in this area and having special division producing and selling membrane bioreactors and studying new configuration, new membranes appropriate for this kind of application. As you can see here, the operating parameters that you have to control when you are working in membrane bioreactors are many if you want to do in the right way. So the system needs really chemical engineering to handle the situation. You have the overall performance of your system is related to the characteristic of the feed that you are sending to the reactors, composition, the pretreatment eventually necessary, the removal of the nutrients, and what you have to do with the water at the end, depending from the exit of for the kind of water utilization, the situation can change. If you want to reuse, so it has to be fresh water or going back to the process, etc. You have to study all the specific biological aspects of your process, because you are combining a biological treatment, the biological degradation, transformation of your feed with separation. So the characteristic of your biomass is in terms of structure of the flock, of this flocculation, the formation of the products that are just produced in the biomass, the viscosity of the system, etc. And the characteristics of the membranes also are quite important, significant. Can be just tubular membrane, flat sheet. There are two kinds of configuration you will see. One is filter press, basically flat sheet membranes. The initial configuration was that one. Kubota is the company in Japan that made the first module. The second one is just hollow fibers. General Electric is using hollow fiber, for example. Kubota is using the flat sheet. And so pore size, surface properties, configuration of the module, geometry, dimension, and all the typical characteristic of any membrane operation that we have been learning, fouling, reversible or irreversible kind of fouling. Critical flux is one of the parameters that you learn has to be well and quickly identified to overall to understand how to design a system. And aeration system, that is a very important one, because if you remember when we have been discussing about fouling, at the end, backflushing and aeration are the two methodology that combined together give the best performance in terms of controlling fouling phenomena, particularly in this kind of situation. So that's why here this aeration has a special attention, because it's a crucial aspect of most part of the membrane bioreactors installed until now. And depending from the frequency, size of the bubbles, and speed of the bubbles, etc., are just important parameters. They have influence on the cost, because you spend money for doing this, but you can solve basically all the fouling problem. And as always in our system, there is not only problem related to the feed and to the membrane aspects, but also problem related to the hydraulics of the system. Retention time and the transmembrane flux and cleaning procedure, etc., are all parameters that have to be tested and analyzed. This is important because, again, traditionally, this kind of work was not done by chemical engineers. Civil engineering was normally taking care of the treatment of the wastewaters. And today, it's a little bit more complicated for civil engineers handle the new way to treat. These systems are much more effective, much more efficient, and they work. A lot of the traditional biological plants were not working very nicely, and it was quite difficult to control the performance, etc. In some countries more than the others, but that was a general problem. Now you have a real reactor, but you need a real understanding of all the problem of reactor engineering, and that is makes the story a little bit more complicated. To give an idea, however, these membrane bioreactors today are already very well utilized and installed. That is the case in a few years ago, in 2006, in North America. You can see that there are many areas in which membrane bioreactors have been installed, and not only for the treatment of the wastewater, but also for the optimization of the process. More and more, we are moving these membrane bioreactors not at the end of the pipe, but upstream, to minimize the possibility to create pollution, to create wastewaters, by optimizing the step just at the very beginning, minimizing the formation of the waste along the production line. That's why you can see there is basically most part of the industrial sector that we are familiar from, electronics, pharmaceutical, automobile, chemical, food and beverage. They have plants installed at that time already, which means basically 8 years ago, but this number is increasing exponentially all around the world. That was when basically the problem was starting. In some cases, these plants, they are not plant huge as reverse osmosis. We are not talking about millions of cubic meters of water per day, but these plants already are becoming of significant size. That means 1,000 or 10,000, 20,000, and today there are 300,000, some of the biggest one, cubic meter per day size of this plant itself. As I was mentioning, first of all, there will be different configuration, but there are some clear advantages in this kind of system, and they are just listed here, that the system is working, much easier to control, to optimize, to minimize the defect, etc. So improved water quality is one of the characteristics compared to the traditional system, relatively lower. When people are talking that membranes are more expensive, these people don't know the story. They want to make propaganda for the traditional system. In fact, the investment for one of these MBR is lower sometimes than in traditional plant that have been installed in the past years. Footprint, logical process intensification much lower, retention time also much lower, and you can reach much higher, you can operate with much higher biomass concentration. You can eventually, studying correctly the system, find a way to reuse most part or part of the wastewater, just recycle in the system itself. And as I was mentioning before, as all membrane operation, that's relatively simple. It's much easier to also to make automatization, remote control, and all these advanced control systems can be utilized. And in this case, also you can just integrate not only a simple separation, but just a purification and separation. That means if you're working in the process, industrial production, in some case, this kind of purification and separation give you the possibility to transform what was before a waste, just to put in the municipal water treatment, in some part that can be completely reutilized in the process, increasing the efficiency, the quality, and the economy of the process itself. That's a typical example of one of these modules with this fiber that is coming from GE, from General Electric, as you can see. As I was mentioning before, most part of the system that you will find in literature, particularly in the early stage, were just ultrafiltration. It was ultrafiltration combined with the biological transformation. Assuming that in ultrafiltration, if you remember, we are discussing a system which here must be a solution, no suspension in ultrafiltration. These membranes are porous, and we have viscous flow, convective flow, eventually Knudsen, depending from the size of your pore. Normally, this porosity here is of the, you can have cutoff of the order of 50,000, 100,000, 1 million thousand. Remember that cutoff means that when I say cutoff 500,000, I'm assuming that 90% of the molecules in solution having molecular weight of 500,000 don't go across your membranes. It's a little bit qualitative definition, but that's the way of doing. But very different than the rejection that is much more specific, very useful definition. But all these membranes can have the capability to have the salts and solvents going across, but all the high molecular weight species don't go across the membranes. So you can separate and purify. And depending from the size of the microorganism or bacteria or other chemicals that are present in the feed solution, you can design your separation. Normally, what is done by ultrafiltration or microfiltration, that traditionally were combined with bioreactors, you permeate metals, aqueous solution, and you just reject all the bacteria, some suspended salt eventually, and so on. So you just also sterilize your solutions, or you avoid any microorganism going through. And that is one of these things. And at the end, you can have some effluent, quite interesting. That's typical case. When you start in a aeration tank with this kind of solution, very high level of turbidity, high, very high silt index, for example, if you remember how we define silt index, but the water that you permeate, you absorb inside the membranes and as an effluent is quite limpid and clear. In some cases, that can be also fresh water that can be utilized. Normally it's not, because here you can have salts. If there is any salts in here, sodium chloride, potassium chloride, etc., would be also present here, because membrane normally is ultrafiltration, so you don't separate the salts. But there is turbidity is basically zero. And again, you can have a reduction, for example, in the production of sludge, as you can see here, more than 40%. And one of the interests for doing this that was not possible years ago is that during the years of this, in which these things have been invented, at the end of the 2000, basically, you can see here, the cost of the membranes that people were telling, membranes can be interesting, you can do separations, but not too expensive, too difficult for this kind of application. From this value, now the cost has been going down and still is going down. That is 2005, but you can see if you go to 2010 or 15 as now, that this cost is still going to, instead of 50, that means $1 per square meters, you can arrive to 10, 15, etc. So this is one of the motivation for looking with more and more interest. It's also interesting to learn the overall cost of this kind of operation, where are they located? You can see here that the most part of the cost of the membrane bioreactor is still related to the cost of the equipment. And energy is the other cost. Membranes, as I told you some other times, are relatively a small component of the overall cost. 8% in this case, in average, this is the value, between 6, 7, 10% most, which means that the cost of membranes is important, but not so important, because at the end, in the big plant particularly, this is only no more than the 8%. So if the membranes also cost a little bit more, the impact is only on the 8% of the total. And but the real costs are the energy that you still have to utilize and the cost of the equipment in the system. Just to give an example of what is happening more recently, that is the case of China. China, everybody is assuming that they don't keep too much control about pollution problem, etc. No more. China is one of the countries that is investing more, and China is a leadership today in membrane bioreactors. You can see here that just when in the other country where they were starting 2006, and there was just the starting day, initially they had not very active, but today they are growing and growing year by year. And already the projection they have is quite interesting. And this is projection not done by a single company, from the government. That's the money that the government is investing to realize these plants all around China. As you remember, when we spoke some weeks ago, China is already creating industrial membrane park, where this kind of system are under accurate investigation with polymeric and ceramic membrane, for example. And that's why all this money is going to be invested. Again, this problem is not just located in the United States or now in China, but basically they are all around the world. If you can see here, if you go in Busan, General Electric has been installing last couple of years ago plants relatively big size. This is plant in Busan is 100 megaliters per day, this peak flow. So these are not more small plants, and this is the average most part of the plants installed from in China, in Korea, in the United States of America, etc., etc. So it's becoming very well accepted all around the world as a logic. Some of the largest plants are produced, as I was mentioned, the big players. This is a General Electric. General Electric years ago had nothing to do with the water treatment or just membrane technology. And one day what they made an analysis. They realized that was one of the most interesting areas to be involved. And they went around the university and small company, and they bought a company. Company was called Xenon. Xenon was a company of a Hungarian professor who just escaped from Hungary time ago, and he went to Canada, and he started membrane company with 5, 10 people, no more than this. And after they start to grow, and he just was the one that, following Kubota, decided this was an area of interest, and he started to produce fibers for combining ultrafiltration with biological treatment. And one day, GE went to this guy, Benedict is his name, that was always with no money in the pocket, etc. And they bought him for $500 million cash by overnight. So from one day to the other, he changed completely his life, becoming people with a lot of money, just selling the Xenon company. Now Xenon, when you see GE, normally GE, Xenon. GE had no technology in the hands. All the technology of GE was the Xenon technology transferred under the name GE. Now there is a lot more action in progress, but the story was a very small company that became part of the GE. And that was just a research company, basically. And you can see here some other big company. Kubota, this is the first company in Japan that invented. This is Professor Yamamoto, who just was the professor at university, but he sold all the activity were related, was taken from this Kubota company. But other than Siemens is another big name, Asahi, Mitsubishi. You can see big players in this field. It's not just a small activity. Membranes can be of different kind. Basically, for the moment, for today, for yesterday, not for today, but for yesterday, the most part of the process I was mentioning were ultrafiltration or microfiltration. And in fact, when you go to see which kind of material has been utilized and still utilized, PVDF, some of you are very familiar with this, both flash sheet or hollow fibers, polyether sulfone. In some case, they don't tell you too much, still confidential, the kind of polymer they've been using, but all the rest except some ceramics are just polyether sulfone and PVDF. Today, the situation is changing, and new polymers are under investigation, including, for example, in Nanyang University, because more and more you are trying to work in a more extreme situation. For example, you are trying to concentrate more what you separate from the water, so you need more hydrophobic membranes, and not only PVDF can be utilized, but some other perfluorinated polymer that we've been mentioning as ALAR or something similar can be utilized. But as you can see here, and this here, that was a few years ago, most part of the membranes were just based on the polymer that are traditional to you. And the pore size is typical of ultrafiltration, of microfiltration, 0.2, or ultrafiltration, 0.04, 0.1. This is the order of system. Until now, no big evidence of the fact that these membranes can be totally different. This membrane can be membrane distillation, or can be nanofiltration. Today, if you want to operate wastewater treatment in some pharmaceutical system in which we have a significant number of some very low concentration of compound that just go in the effluent, not easy to, you cannot separate by ultrafiltration and microfiltration. You have to separate with nanofiltration. And there are new groups, new company, research company, or a large company that are studying nanofiltration instead than microfiltration and ultrafiltration, and eventually nanofiltration system, that means much lower pore size here, stable in organic, not in water, but in organic system. And that is the most advanced logic. If you go to a company as in Europe, Evonik, for example, or the people researched in Imperial College in UK, just working, changing this list here, making nanofiltration, not only nanofiltration, but nanofiltration for non-aqueous solution, and that will be a significant progress in possibility to optimize and to redesign most part of the polluting system that we still have today. And the people, we are aware, but people cannot talk too much because we don't have the solution. Genotoxins are very low molecular weight compounds, relatively low, and they are present in a few ppm, so not very important. You don't see anything now. You will see the effect in 10, 15, 50, 100 years if we don't find a solution. And that will not be ultrafiltration, but will be basically nanofiltration, or in some case, membrane distillation. Just to show that the system that I was showing before are all, as example, flat sheet membranes, filter press, just a traditional filtration system, and all this kind of, and that basically was General Electric was the main company doing this. But you can have exactly the same story with hollow fibers. And with hollow fiber, there's much more research activity today because you have to optimize the property. The hollow fiber that you have to use here are a little bit different from the one you are using for gas separation or for traditional ultrafiltration. They need a much higher mechanical resistance because these hollow fibers are floating inside the solution. They are free. They just are free to move inside these bioreactors, and you have to control the fouling by a lot of by mechanical system, bubbling air. So the mechanical property has to be much more significant. That's why researchers are working to optimize fibers specifically for membrane bioreactors application, basically. Also in this case, however, the material you see is all the same. It's basically PVDF, hollow fibers, or these polypropylene sometimes. Polypropylene is relatively low hydrophobic character, easy to lose hydrophobicity and becoming hydrophilic, but basically these are the same kind of system. Also, hollow fiber are just polyether sulfone is also utilized, Teflon, in some case where you need some interesting, Sumitomo, as you know, is a very big group, and they have a specific application, and for them it's important to have very efficient separation, so you can also spend money having microfiltration, 0.2 micron, 0.1 micron, but very hydrophobic material. And that's because they know what they're doing, and the cost of this Teflon, as you know, is normally expensive. And if you can use polypropylene, it will cost 1/10 than Teflon. But for some application, these kind of membranes can, the money that you're spending is just good money to be spent. Basically, all the material roughly the same. As you can see here, the size of the plant starting to increase. 1,000, 2,000 square meters installed, 1,000, etc. They are not huge plants because they are process plants. They are not plants only at the moment to treat the waste. In some cases, they are just along the line, so you don't need too big installation. Remember, we have been discussing that the major problem when you are working with this kind of units, we are working with wastewater, so the traditional fouling problem we have been discussing are much more severe in here than in any other application. So the understanding of this effect of some of the bacteria which can be present in this solution and that can be absorbed 1, 2, 3 initially on the membrane surface without any real problem, so you don't realize what is happening, and so you just go on working. But these bacteria, with time, they will start to proliferate. They can find nutrients, and they grow, and they start to transform the initial 1 bag, 2 bag in a biofilm that can cover, not coming from the feed, but coming from the growth of the bacteria absorbed on the membrane surface and from the nutrients that are giving strength to the bacteria, and they form this biofilm on the membrane surface. Biofilm, as we discussed already, is a very interesting general problem. There's a lot of biofilm in our body. There are biofilms in a lot of natural phenomena. how to understand, how to control is complicated, but this biofilm is at the origin of biofouling. It's not just the traditional fouling that is important, because traditional fouling, in this case, is also present, but can be minimized. So we have just the fact that we are just extracting the water and combining a kind of mechanical cleaning of the membrane surface by all this bubble moving along with the traditional way, giving some good possibility to minimize fouling. That's why we have so many plants installed. Ultrafiltration has been very well established for the fouling control in this case. And you can have, as you remember, irreversible fouling is the bad one, where you can have something inside the pore, very difficult to clean the fouling when it's taking place inside. On the surface, it's relatively easy with a physical cleaning. The real problem, however, is when you arrive to the situation in which the biofouling is becoming significant. Here is just you remember the different steps we've been discussing in the initial stage. Initially, we have a clean membrane, and you can see a relatively fast transmembrane pressure increase for a short time. There's evidence that something is creating a deposit, so you're increasing the resistance to the mass transfer resistance. And after you have a relatively linear increase of the fouling, that means decreasing of the transmembrane flux, and you can have also a situation in which at the end you start to create different deposit on the membrane surface, and you have a sharp increase of the transmembrane flux, the decay of the transmembrane flux, or in parallel increasing of the pressure drop across your system. And basically this is related when you have this EPS. This EPS means extracellular polymeric substance. These are the one that can be produced during the process itself. They are initially not present, but during the process they can be produced in the system, and that's the one that is not easy to control and are at the origin of the biofouling at the end. And the way to solve the problem, just to remember, was just backflashing and ion scoring. These two combined together is the best way from the one that we know today. In the future, somebody will make something better eventually, but that is the problem, that the way for solving the most part of the problem. What we are not able to solve today is this understanding of the microbiological effect that we have during the process, and the most interesting study today are suggesting to work on this quorum sensing mechanism. If you remember, that the idea is that if you understand which is the biofouling mechanism, which are the bags that are just interacting each other and growing and forming the biofilm, you can try to identify which are these other molecules able to block the communication between two different compounds. So if you just stop the communication, you can avoid the growing of the biofilm on the membrane surface. That is a Korean invention. The most part of the initial work was done here in Seoul at the National Seoul University, and today is one of the most interesting, attractive way of doing, and you have to learn a lot in terms of microbiology, because this quorum sensing mechanism means that you have to understand which is the microorganism that is really affecting and growing as a biofilm. And they can be different if you're working in a food industry or if you're working in petrochemical industry, etc. So it's not a general, it's a general methodology, but not a general answer. You have to identify, so you have to learn a lot about microbiology, basically. But this system works, and this is one of the ways in which you can realize your system. This is a system where you have hollow fibers. You know, remember, normally you are used to take hollow fibers and to block them in a module. In this system, they are not blocked. these hollow fibers are free for moving. It's a better way to control the fouling on the surface. Helps. What you are doing here, and in the meantime, you have making the vacuum inside, and that is the bubbling that you just, the airflow that just helps to remove any deposit and to create turbulence and to avoid increasing of the boundary layer on the external membrane surface. Remember that what you are doing here is just to extract from the inside of the fibers the clean water and to concentrate outside the waste. That is the high diffuser is a very important component of the membrane bioreactors. There's a lot of work how to make the efficiency of this bubbling, the size of the bubbles, and compared that is an energy that you have to spend for cleaning at the best this membrane surface. The quality of the polymer, as we discussed already, are quite important for the fouling control. That is the case that you're mentioning, the difference between the polyacrylonitrile, PVDF, and polyether sulfone. And that is what they call the most traditional material for the ultrafiltration membrane preparation. And you can see here that the affinity for acrylonitrile is lower than the one of PVDF and lower than the one of the polyether sulfone. Today, there's much, much more attention to the preparation also in this specific case as of inorganic membranes. Motivation is that inorganic membrane in principle is not really real what is happening, but in principle they can be much more resistant. They can work at high temperature, and that means you can just reduce part of the fouling problem, just decreasing the viscosity and making the control of the system. Mechanical properties are higher, so you can have superior hydraulic, thermal, and chemical resistance, etc., etc. However, the cost of these membranes today is much, much higher than the one in polyether sulfone and polyacrylonitrile, so you must be careful. Plus, inorganic membranes are not so resistant as people are assuming. Are resistant with nothing happen. But if you just they fall down, they break. Polymer don't break. Well, every time you make you shut down or start up your system, you can induce vibration, and sometimes if you don't do correctly, you can break the system just by inducing some vibration in the material which are relatively brittle and much less flexible than polymeric. So it's not the cost can be quite significant, not only in terms of initial cost, but in terms of running cost. And that's why the inorganic membrane that in principle can be interesting are not so interesting in real life. You will find here in Korea, 90% of the plant installed are polymeric. Very few are inorganic. So if it's not just a situation which you have to work oily solution or very viscous solution, you have to work high temperature. In this case, inorganic is the only way of doing. But if you can avoid inorganic and going with polymers, it's much better. The story of the quorum sensing we discussed already, and just remember that is one of the interesting innovation to be introduced in these membrane bioreactors, because that will minimize fouling, because where we know how to do it, but biofouling where still we don't know too much. And the reason for which we don't know too much, because membrane people had no experience in microorganism population dynamics, no idea. That means we have no idea how this propagation and growth of microorganisms take place. And we don't know too much about morphology and physiology of the bags. And we don't know nothing about the quorum sensing mechanism. Now these things are becoming part of the know-how and study that students have to learn if they want to innovate and make progress in MBR. And that is quite interesting, and it can be one of the possibilities. That's here just to tell you in general where we are with this kind of system in the last, which are the prediction. You can see here that everything, people are quite optimistic. They are talking about billions of dollars in the next few years. And we are still in the developing stage. We are not just in the basic. You are just in this area here, so still a lot of work has to be done, but the growing is quite fast. So this is the introduction to the problem, just to show you what is happening in one of the fields much more successful. There are thousands of these plants, relatively small, etc., but growing very nicely. However, these membrane bioreactors are not just for the treatment of wastewater, but can be much more than this. And in general, they have a lot of potentiality. Now, I was mentioned before, the progress that we had in the wastewater treatment is because these ones are not just pot where you put microorganisms, you mix and something happens. These are real reactors. So you need expert engineers, chemical engineers, who have to understand how to handle reactors, basically, and not just a traditional biological system that was before, which makes everything a little bit more complicated. And for doing this, you can just have to look again how the system is working. So again, remember we are talking about a reactor this time, reactor combined with membrane operation units, or reactor with membrane acting as catalytic and separation units. The two things are very different. You can have a system in which the membranes is the external one, but system in which is not only the one that we discussed before, where you have this configuration submerged in the reactor. You can have many other possible configurations for realizing your system. This is one of the most interesting. The membrane is the reactor, because you can have a system in which you can immobilize your catalyst. Again, membrane biosystem, that means your catalyst is called enzyme. They are protein normally, but you can immobilize your enzyme inside the micropolar structure. And that's another very interesting case. And again, this is one of the cases applied industrially, particularly in the biotechnology, in pharmaceutical industry, in biotechnological industry. And is one under investigation for a lot of interesting situations. Basically, one of the issues is that biocatalyst enzymes normally are a very short lifetime. They operate in a very narrow boundary condition. Normally, the specific activity of an enzyme is, if you just plot the specific activity as function of pH or function of temperature, you are going always through some very typical curve, which a very narrow range for the highest value. So if you just operate for any enzyme at a temperature which is not the one optimal, does not work, a very low specific activity. The lifetime is becoming very, very short. If you change the temperature out of a certain range, the enzyme does not work. The specific activity is going down. So they're very narrow range of performance, optimal performance. So you have to know. When you immobilize, most parts of these phenomena are much more positive. Your lifetime can be hours normally, can become months. If you mobilize urease or some other protease, you can work for months in this when they are not present in solution, dissolved in the solvent, but they are blocked in a phase. In this case, can be just a membrane. Can be also normal column, can be just beads and you block on the beads. But membranes is one of the possible new catalyst design, how to design the catalyst. And that is one of the configuration for a reactor with membrane acting as a catalytic and separation unit inside the system itself. The performance of the system is traditional now, we've been describing already. Keep in mind that when we are talking about this system, enzymes are very special catalysts. All our life is based on enzyme. We are full of enzyme. All our proteins are enzymatic. Enzymes are catalysts with very, very specific in their activity. They just only convert some substrate in products, very narrow range of operation compared to traditional catalysts, metals, etc. However, they have a very high reaction rate. They have very high level of specificity. They just operate in some case. And they can also have what is called here geometric specificity. They can be enantiomeric. They can be able to separate this stereochemistry is very much related to the utilization of enzyme, of the enzyme properties. And that's why they are quite interesting. The stereospecificity is one of the problems that we have been already mentioning, and that is quite important in drugs, but can be important also in many other food applications. Normally, however, they have to operate in a relatively mild condition. They can have very high reaction rate, very high specificity, but very narrow temperature range, very narrow pH condition, for example. So you have to know exactly. And on the other side, they can have very specific interaction. What you have to study normally, if you want to design a system of this kind, you have to model your reactor in such a way that you can predict production rate, selectivity, and how to control it. For doing this, the traditional engineering approach has to be followed. You have to study all the physical aspects and all the kinetics of the system. Today, however, kinetics is the most complicated part of the story. Today you will see that if some of you is working in, or will work in membrane bioreactors, you are always starting for the traditional equation, the kinetic expression already existing, not in this system. In this system, these are typical heterogeneous catalysis, because we are just immobilizing the enzyme on the membrane surface. It's very different than the traditional homogeneous catalysis. And the membrane itself, combining conversion with some separation of some of the components, can have an influence on the kinetic expression. Very difficult to anticipate the results. So what is happening today, that when you make this kind of study, you introduce the kinetic expression that you find in literature for traditional reactors. And in general, they work, but not always. Some cases you have to study again all the kinetic aspects of the system. You can also here work in a typical batch reactor system or in a continuous one. We don't like too much to work in a batch reactor, as you know, because we say that the membrane is able to introduce, to make any process continuous process. We discussed last time on crystallization as a continuous crystallization, etc. This is a typical case also here. So normally, most part of the reactor we are utilizing are different from the batch system, batch fermenter or batch bioreactors, and are just a tubular system. And that's a typical case in which we are working, in which if you just plot the transformation, the changing the concentration of your products in the function of time, you will have this kind of behavior. Well, you have a startup period, and after you arrive to your steady state. And the variable that will control the system are just the feed composition, temperature, pressure, pH. Much more than the normal reaction, because I told you that the lifetime, the performance of your catalyst is very much related to this kind of parameter, to the point that if you make a mistake on the temperature, you destroy your catalyst. Few catalysts can operate at high temperature. They are called thermophilic. Normally the catalysts in our body, they operate no more than 37 degrees centigrade. That is body temperature. If we increase too much the temperature, you can destroy them irreversible. And that is a problem, and some diseases are related. Few cases, if you go in a volcano in nature, where the temperature is very high, and sometimes also chemistry is very high, that means sulfuric acid, you can find special protein. They are called thermophilic materials, which are very special membranes. These microorganisms, these enzymes, in nature they are coming from some microorganisms, and they have a membrane that protects them. The normal membranes are the typical bilayer, phospholipidic biological membrane. You are familiar. Few of them growing in a very special environment, volcano, in the bottom of the sea or in some volcanic area. If you go in Italy, in some area there is volcans. Near this volcano you can find microorganisms that grow in sulfuric acid at 150 to 100 eventually degrees centigrade. They are thermophilic material. Very interesting, very useful for some of these applications. very expensive and very small biomass. So you have to learn how to grow this kind of new enzymes. This is an interesting field, quite expensive, very good specialists, but years ago we were working with some Sulfolibus sulfataricus, which was just one of these microorganisms extracted from a volcan, from the Vesuvio near Naples, where you can find some of these microorganisms living in sulfuric acid at high temperature. And that's quite interesting for some specific application. Here you can see a list of a lot of potential application of this catalyst. This enzyme means a biocatalyst. You can see here that depending from the protease, lipase, amylase, you can just remove greasy stains such as frying fats, butter, sauce, etc. Or you can have cellulase to crush wine grapes. So it means agro-food is one of the area, but you can go to alcohol industry or I think many other ones. So there's quite a large spectrum of possible application. And however, you just have to find solution to some of the problem. Some of the problem is just this one. You have to find a way to immobilize this enzyme if you want to use them. Otherwise, they have very short lifetime. And the membranes can just give you this possibility combined with a significant increasing of the lifetime. Again, here there is some of the motivation for which people, particularly in biotech, as I was mentioning, are working in this field, and you can see interesting possible application in pharmaceutical, and that's basically, if you go in the literature today, you will find different work where we are producing at ITM, people are working on the production of some compound with a very high enantiomeric composition. Enantiomers normally are 50-50, level form, right form. One of the two I was mentioning is the active one. The other one eventually can be negative or not useful. Today, you can produce in some compounds 99.9% of one of the two enantiomers. And that's quite interesting. Using a kind of immobilized lipase is the case in some membranes that are doing a very nice job. Aspect number one, that's why, is how to make this catalyst immobilized in the heterogeneous system you are producing. There are different ways of doing, not only one. And also you have to decide which one is the best, as is part of the action of the researcher, of the good researcher. You can find in literature different way of doing, and you can, in some case, you can just have again the enzyme in a separate units, as we discussed before, or in specific related to the membrane itself. You can entrap the biocatalyst in the pore of ultrafiltration, microfiltration membranes. You can just gellify. The problem of jellification that we studied in ultrafiltration can here be utilized. We had a patent years ago in which we just making the ultrafiltration of a biocatalyst system in a membrane of the appropriate size. You can block all the protein on the membrane surface, increase the concentration to the point that you change state, it becomes a gel. And that's a gel layer. In this case, can eventually decrease, if it's not too thick, can decrease the flux, but it's a catalyst that has a lifetime of months, and you can operate, and when you stop the ultrafiltration, it will be basically, you can recover and reuse eventually. So that's another way of doing it. Jellification, that was continuous immobilization of your enzyme. Or you can just chemical combine with membranes. You can use some compounds, normally bifunctional compounds, glutaraldehyde, sodialdehyde, etc., that you can just block on the membrane surface. If you can avoid blocking, because normally blocking can change a little bit the specificity of your enzyme. So it's better to try to avoid as much as possible, but it can also be done. You can have some cross-linking or some support binding by physical absorption. Covalent binding, avoid, because covalent binding for sure will change the specificity of your enzyme, but that's the one way that you can find different way in literature. And if you do this, you can have shortly from the first experiment that you do in your lab for some specific transformation, which we showed before, to pilot scale and industrial application. So this is an area in biotechnology and in pharmaceutical and food in which we have big system where ultrafiltration or microfiltration is working for producing something that you have in your pocket you don't know. If everybody is using, for example, some ibuprofen is a typical anti-inflammatory drug, 90% of ibuprofen produced today is going through this ultrafiltration membrane system, where enzymes are blocked in one step of the production, not only waste, that is just the production line. That is a typical example of what the kind of interaction you have to realize in the system. And this is some of these applications already existing in these hydrolysis of starch, fermentation of sugars, and hydrolysis of pectins, fermentation of bulgaricus, that means to make some cheese similar, and so on. So you can have a nice, interesting list of different kinds of applications. As you can see, most of them are just food or drugs, the one in which this system are working. These are the most interesting one, production of an antiomeric amino acid. As I mentioned before, you can have some situation in which you can just have specific deformation, one of the specific and antiomeric, which is one of the major problems we have today, and that can be the way of doing. And this was one kind of configuration, but you can invent many other ones. There is other kind of membrane bioreactors in which instead of blocking the catalyst, the enzyme, in the membrane structure, you can just segregate in the membrane module. So you have your membranes in here, but in the shell, between the vessel, the external container, and the membrane, you can segregate, you can compartmentalize your enzymes. So they are not heterogeneous in this case, they are not blocked inside the membrane material, but they are just blocked in the vessel that you are using. And that is just changing the situation. These are quite interesting for some application in artificial organs. Most part of the hybrid artificial organs are based on this kind of system. For example, in the bioartificial pancreas, you can have what is called the Langerhans islets, the one producing insulin, and these Langerhans islets are just blocked in the external empty space in your hollow fibers system. And so they just produce your insulin in this way. That's typical interesting reactors in which you have the enzyme are free typically in solution, and the product and substrate are present in the same system. And that can be the same. You see, most part of these are just what we call hybrid artificial organs. That means the cell, the bioactive compound is a real one. It's coming from humans. It's not artificial. All the rest is artificial. So you just trying to, this is way for hepatocyte in your liver metabolites, and is true for what we call for artificial brain, where you have the neural cell, or for Langerhans islet, that is the case of insulin for the pancreas, and that is artificial liver. That is again a case in which you can just segregate within the pore. And that's what the story here is basically, sorry. For increasing lifetime of your membrane. That's the one that I was mentioning before, where the catalytic membrane bioreactors has a biocatalyst bound block on the membrane surface. That's another configuration, quite interesting, and normally hollow fiber are the ones that are utilized. I was mentioning one thing before. Now, if you want to understand and to predict what can be done in this kind of reactors, you need a kinetic expression, how your catalyst is working and transforming in function of time, concentration, etc. In principle, you have to develop your own kinetic expression. Quite difficult, you have to start again. So people today are starting from a traditional equation characterizing the biochemical conversion you have in a traditional system, in homogeneous reaction or in a system where membranes are not present. For example, you will find in literature that the Michaelis-Menten equation is the one that normally has been utilized. The Michaelis-Menten equation is giving you this kinetic expression, where you have the conversion degree, this is X, multiplied for the substrate. In biochemical transformation, the feed, the component, the reagents are called substrate. So it's just a different term, but means the same. What is a substrate is what you call normally reagent. And so the substrate feed concentration, and what you have here is what is called Km first, is called the Michaelis constant. K is the enzyme kinetic constant, reaction volume, and flow rate. This relationship is a typical relationship that you have and you can utilize when you have your substrate that is entering your membranes, found the enzyme, the catalyst, make the conversion, and go out as a permeate. And if you utilize this is the kind of plot where you can have this initial reaction rate as function of the substrate concentration, and you can define in this case this Vmax, that is part of the equation up here, and what is called half-life time, and that is equal, this basically is related to the Michaelis constant, when the specific activity of your enzyme is half of the total that you can have. So this is typical expression for the substrate reagent conversion in a biochemical reaction. Just to show this for only one reason, that very often you have to be sure that in your membrane system, this equation is still valid. Michaelis-Menten has nothing to do with the membrane system. Membrane systems are introducing some new factors, that you have chemical conversion, but with continuous separation of some of the components. And how these components can have an effect on the kinetic of the overall reaction is not so clear. As you know, when you're writing any equation and you write your kinetic expression, what you write on the blackboard is only the total final description of your reaction. If you write here carbon plus oxygen giving CO2, that is apparently one reaction. If you study the kinetic expression of this carbon transformation in CO2, you will learn that there are 5,000, at least 5,000 steps from carbon plus oxygen arriving on CO2. The kinetic is much more complicated than expected. Here we have this equation, and when you change the system, some of these steps in between, the initial step and the final one, can be modified, because you can have interaction with the membranes itself. You can have some components that are permeable or not permeable in the system, and this changes completely the overall system. So you have, in principle, you have to rewrite and to carry on again all the study that Michaelis-Menten made for a long time, which are the different phenomena that take place in our system when membrane with certain level of selectivity is present. Very difficult. Until now, most part of the people are still using the Michaelis-Menten expression, assume it's valid to predict the final performance and to be utilized as a kinetic expression also when we have membranes involved. And that is, in most part of the case, it works, so the effect is not so negative, but this is not very general, so people have to be studied again. I'm telling this because when we will discuss on the same membrane reactors in a gas phase, for example, for gas separation, high temperature, it is an area where engineers have been much more active in trying to redesign kinetic expression of steam reforming or water gas shift, etc., when membranes are present. And this is not yet the case in bioconversion. Just to remember that everything we have been discussing at the moment has been applied combining conversion, chemical conversion, biochemical conversion, with microfiltration and ultrafiltration. But today, there's no reason that we have to stop here. Now that you know what is nanofiltration, what is solvent extraction, or what is the other units that we have been discussing, you can recombine the chemical conversion with each one of the membrane operation that you have in mind, if you know how you can have an influence on the overall reaction at the end, what you can eliminate, what you can separate, etc., etc. Obviously, the membrane materials is also very important. And here what we can summarize today, advantages and disadvantages. The advantage we have been discussing already, disadvantages are that it's not easy to reproduce these things at very large scale. One thing is in the lab, but if you have to go for different reasons, the one I was mentioning before, including the understanding of the kinetic expression, not so easy when you have to scale up on large scale. And again, membranes is giving some benefits. We learned that it's giving increasing lifetime, for example, or making the separation. However, this is, again, a resistance that we are introducing of this system. And when you combine, particularly when you make a chemical interaction between your catalyst and the membrane, you can have a decrease, in some cases, significant decrease of the specific activity. So you have to be sure that the advantages that you have here are combined with the fact that this enzyme is still active or not. In some cases, it's not always a positive system. Just a few slides more from what we will discuss another time, but in general now that you can see that the reactors can be much more than just bioreactors, much more than the one we have been discussing until now, relatively simple. This is a typical kind of membrane reactors, no more bio at this point, where you can study any kind of important chemical transformation in petrochemical industry, in any chemical industry, using the same concept, basically. And that is one of the typical transformations in which you have what we call these multifunctional reactors, where you can carry out a reaction and separation in the same vessel, and more than this. And that's in this case, you can see you have a system where you have this tube inside. Externally, you have your vessel, and inside there is another tube, and this is permeable. For example, if you have the catalyst outside the tube, put here, and you have just your putting in some gas, methane, for working on steam reforming, and this system and the catalyst is able to induce the transformation of your gas in hydrogen, CO, CO2, etc. If this tube inside is a membrane, selective membrane, for example, is a palladium membrane, what is happening is that during the transformation of your reagents due to this catalyst in the outside part of the tube, hydrogen is going to be performed. But this membrane, as you learn, hydrogen, if this membrane is made with palladium, hydrogen is only going through the palladium. All the other component, the gas that we are supplying as a reagent, the CO or CO2 or water that we are forming will not penetrate. So we can remove continuously the hydrogen from the reaction vessel. That means you will perform an interesting system where 100% basically of your product can be converted. This is the basis of one of the most interesting studies in the last few years for the steam reforming and trying to produce hydrogen on large scale using this kind of system. There are hundreds of millions of dollars being spent, particularly using also not only palladium, but perovskite, for example, membranes, in this kind of configuration. Not easy, a lot of work, and no big plant already realized, but again, this can be done. And can be done in water gas shift, in steam reforming, in esterification, dehydrogenation, in any the other reaction, nothing related anymore to catalyst, to biocatalyst, to enzyme. So with enzyme, the system has been already successful. Costs are much more less important in enzyme. In this big system, situation is a little bit more complicated. So a lot of work. If you go in literature, you will find a lot, but a little bit more complicated to realize. But what is important that if you do this, you will start to realize that your enzyme, your membrane reactor, can do much more than just remove one product from the reaction volume. You can use your system as a selective separator or extractor. That's what we were talking about. If you have A and plus B, that's going to transform in P, and you are able to remove one of the components, that's quite interesting. Never approach reversible system, never approach equilibrium. But you can do, if you are chemical engineers and you know how to handle reactor engineering, you will realize that this kind of system can have some more interesting opportunity. For example, you can use the same system not only to extract something, but to distribute something. That means membrane operation as a distributor. So you can avoid hotspots, big high temperature variation, etc., by just controlling the supply of your reactants to the reaction volume, to where the reaction is taking place. So that's an interesting other application. Just how to supply the component B to the reactant, to the reagent A, and just to avoid excess of the component eventually. And that can be done if these membranes will be selective, the same story before. If we have to supply hydrogen, instead of making just the hydrogen in the system, we can supply hydrogen through this kind of system in the specific amount necessary at stoichiometric level eventually. So you just avoid any side reaction, any temperature variation, etc., etc. So you increase security of the reaction and so on. And you can just operate as a contactor, as we discussed. That means no selectivity, but just if you have, for example, organic solvents that on one side and aqueous on the other one, and you don't want to have the two in contact for poisoning a phenomenon, etc., on your catalyst, that can be done. And that you can have just using as interfacial contactor or force flow through system, etc., etc. So there is many opportunities in which you can modify the way to carry on any traditional chemical reaction. This kind of work is going around, if you go in any center of catalysis around the world, in Dalian here in China, or in Novosibirsk in Russia, or here somewhere in Korea, etc., you will find experts today working how to redesign what they call a catalyst design, how to redesign reactors, assuming that you can use your catalyst in a different configuration now, as realizing this kind of system in membrane reactors, where you can use your catalyst in a system where you can have a selective separator extractor and a control supply, or just a very ideal contact between different reagent species that you are forming, and so on. And again, this will be realized in a different kind of configuration, where you can have just inert membranes, and the catalyst can be just packed on the support, as I was mentioning before, in these tube-in-tube reactors, or you can have just a support, and the catalyst can be dispersed in the membrane itself, or you can have just the membrane that is a catalyst. You can form a membrane with a catalyst material. So you can have a lot of possible way of realizing these kind of things. And keep in mind that, however, if you do this, here are all the possible benefits, advantages, etc., and most parts of these are not being explored yet, by the way, you have to start to redesign also the kinetic expression, because all these kind of phenomena that are taking place here are just also able to modify the logic of these 5,000 reactions that I was mentioning before, which are the ones that are taking place before arriving to the final one. So let's stop here, and we will eventually continue.